dubstep, like the type of music. Well, I bought a shirt yesterday that said, "I really love you, but I've chosen dubstep over you."
Not what I had in mind.
There are
Or like the big, like the one that comes right here.
You should try them out. They're crazy.
Mark, 149. Number 10.
I woke up early. I know.
Here's
He never texted me back.
But with that, I was
Well, I texted him like this long essay, like letting him like, maybe you should tell me that I'm with somebody because I don't really know what I'm doing.
Oh, I just got
there's that one girl.
But
He must have first.
Well, I know, I did it everywhere.
Yeah.
It's like zero up on the board.
So, minus
But I'm like,
50.
I don't know.
Yeah, minus
$60. I'll just stick to Carmen. I would say something.
Are we live, by the way?
Yes.
Sweet.
We're live.
Yeah, that. Oh, it's like, maybe I don't say it. Live. It's Saturday Night Live. Oh, it's probably
A smidge of review. We developed many equations that express relationships between 4 major gas variables. Pressure, PS, test question, what is pressure? Like, be articulate, be clear, what is pressure? Pressure is bombarding particles on the container. Like, if you don't have a container, you can't have pressure. You're gonna need to get a paper towel of water if you want to go away. So yeah, bombardment of particles against a container. If there's no container, if there's nothing to bombard against, there's no pressure. Think about it. It would just be like a particle going down like a tube. Like, no resistance, no force, no pressure. Okay, volume is another variable. Number of particles and temperature. Temperature always measured in Kelvin. If given Celsius, you always add. All right, great. You can start combining the gas laws together. This is a common one that you'll see, sometimes referred to as the combined gas law. And if we put all 4 variables together, we end up with this guy. And this is where it feels magical, because this result, PV over NT, is always the same thing. We call it R for the ideal gas constant, of course, which is 0.0821 liters times atmospheres over Kelvin times mole. Units are critical when it comes to what constant comes out of that equation. If you solve that equation generally, if I take this guy here and I solve him generally, just cross multiply basically, you get PV equals nRT. The biggest thing to remember about R is the units. That can catch you. Now, we also used the Pervner equation to come up with another fact about gases, and that's this. At standard temperature and pressure, you give me 1 mole of a gas. I don't care what gas it is. I don't care whether it's hydrogen. I don't care whether you just farted and it's methane. I don't care whether you just exhaled and it's carbon dioxide. I don't care if you want to sound like the guy from Saw and it's sulfur hexafluoride. You give me a mole of a gas, 6.02 times 10 to the 23rd particles. You put me at standard temperature and pressure, that's 0 degrees Celsius and 760 torr. And that will take up 22.4 liters of space. That is a constant. 1 mole, 22.4 liters. Now, what that allows us to have is a relationship between quantity and volume when it comes to gases. Now, we can step this up into equations. Here's an equation. CH4 plus 2O2 yields CO2 plus 2H2O. CH4 is actually the methane that is produced by the bacteria in your colon that is present in your farts. It's also what comes out of your gas stove or
A cow's
gas
behind.
furnace, a cow's behind as well. When you mix it with oxygen, you can burn it, and basically when you burn the methane, you make carbon dioxide and water. This is, in fact, a combustion situation, but that's not what's important. What's important is, well, first off, is this equation balanced? Just give yourself 30 seconds, 45 seconds, take a look at it. Are we balanced? We are, yeah, we are. Okay, so they gave us a balanced equation. Now,
Bless you.
since this entire discussion this semester has been about gases, and it would be nice to take advantage of these facts about gases, it would be nice to know what in this equation is a gas. Because if we have a gas, we have regularity. So, one thing that you will notice with the equations that you will encounter in this chapter and on the tests and when we're talking about gases is it is common to put in parentheses after something what state of matter it is, whether it's solid, liquid, or gas. And if I rewrite this equation, it would read like so. CH4, gas, plus 2O2, gas, yields CO2, gas, plus 2H2O, gas. Now you might say, whoa, wait a second, oh, actually H2O is liquid. There we go, that sounds right. That sounds better, doesn't it? Yeah, liquid water. Okay, we're all good. Now, the nice thing about the gases is they act regularly. So every time you see a G, a little part of you inside should get excited. Because you know that 1 mole equals 22.4 liters. You know that there's a relationship between quantity and volume. So, remember, back in the day, we could have a problem like this. Given this equation, we could say, if there were 8 moles, bless you, 8 moles of CH4 reacting in this equation, how many moles of H2O were produced? This is a question from last semester, the end of last semester. This is what we were last dealing with. Consider the equation. It says we have 8 moles of CH4, and we want to know how many moles of H2O. Now, as I solve these problems, I've told you what I tend to do. I tend to write 8 moles under the CH4, and I tend to put a question mark moles under the H2O, just so I remind myself of what I have and where I'm going. But there's a relationship between the moles here, because for 1 particle of CH4, I make 2 particles of H2O. Well, run that 6.02 times 10 to the 23rd times, and then you'll have 1 mole of CH4 making 2 moles of H2O. Let me write out that relationship. 1 mole CH4 equals 2 moles H2O. Let me show this another way too, because we did this last semester and it didn't sink in perfectly with everybody. Let me try a different way. Rather than doing it with dimensional analysis, let's try ratios. The ratio of CH4 to H2O is what? 1 CH4 to every 2 waters. How does that look? Does that jive? CH4 to H2O is 1 to 2. Why? Because there's 1 CH4 for every 2 H2Os. Does that jive? Now, let me go with this now, because this is a new way of looking at the problem. The question was, now this fact, let me just say clearly, this fact that we wrote here about the ratio was only taken from the equation. It had nothing to do with the fact that we had 8 moles of CH4. But now that we know that we have 8 moles of CH4, we can plug in and say I've got 8 moles of CH4 and play algebra. This may feel easier. It already feels easier. I feel like this is like effortless compared to what we were doing last time. Cross multiply. H2O equals 16. 16 watts? We were talking about moles, right? How does that feel? I like it too. I've never done these problems these ways, but man, it's a good idea. Somebody mentioned, I think, that when Mrs. Richardville was here, you did these with ratios. And when I heard that, I thought, ding, light bulb. The ratio of CH4 to H2O is 1 to 2. We know we had 8 moles of CH4, solve it out. 16 moles of H2O, doesn't that make sense? Because for every 1 of these, we produce 2 of those. So for every 8 of these, we make 16 of those. Kosher? Now, here's the neat thing about it. I know I can always ask questions about moles because the numbers here relate to quantity. But if I'm dealing with gases, moles and volume are intimately related. So if I'm dealing with gases, I can ask the same questions in terms of volume. So here we go. Let me ask a follow-up, another question relating to this exact same situation. If there were 20 liters of O2 reacting in this equation, how many liters of CH4 were necessary to also react? Question. Different problem. I'm not talking about moles here, I'm talking about liters. But so long as we have gases, moles, liters, interchangeable ideas. They're directly related. They're intimately related. So this is a different problem, but we can use the same relationship. Why? 20 liters of oxygen. Oxygen's a gas? Yay. That's good. That's helpful. We asked a question about how many liters of CH4. CH4 is a gas. Also, yay. We're dealing with 2 gases, which means we can take advantage of this fact. Which means we can take advantage of the fact that 1 mole is 22.4 liters. So let's take a look at this problem. What's the relationship between oxygen, 20 liters of oxygen, and CH4? Oxygen to CH4 is in a relationship of what to what? Oxygen to CH4, just to make sure we're all on the same page, oxygen to CH4 is 2 to 1. This comes directly from the equation. Now bring in the information. It says there were 20 liters of O2. Okay, 20 liters of O2. Here's my O2, put in my 20 liters. I still have CH4 in my equation, but that's great, because that's what I wanted to find out. Due to multiplication, you get 2CH4 equals 20. You get CH4 equals 10. 10 what's? In this case, we were dealing with liters. Boom. Take a moment to step back. 20 liters of oxygen. And we said 10 liters of CH4. Does that jive with you? You needed twice as much oxygen, so you're going to need twice as much volume of oxygen. You needed half as many CH4s, so you're going to need half as many liters. Why were we able to play the same game with liters? Because we had gases, and gases act ideally. Why? I can't answer that question. I don't know if anybody can answer that question. But we don't have to answer that question. All we have to do is just act under the assumption that the gases do act ideally, and then play chemistry. Perfect. Let's do another example. Ooh, here's a fun one. (3H2) gas plus N2 gas yields 2NH3 gas. One nice thing about every equation you'll encounter from here forward, they'll give it to you balanced. Because you've proven that you can balance equations, right? So now we don't have to waste our time doing those childish games. Because that's basically what it is. Balancing equation is like a childish algebra game, right? I mean, if you wanted to, you could probably train a 5th grader to do it. It would take time, it might take a month, but you could do it. So they're going to give you the equations balanced. Let me ask you a question about this. Okay. 5 liters of nitrogen combines with hydrogen to form how many liters of NH3? Question mark. We have 5 liters of nitrogen, and we know it's combining with hydrogen. That's in the equation. And we're forming, the question now is, how many liters of NH3? So we're dealing with nitrogen, and the question is about NH3. So 5 liters of nitrogen, how many liters of NH3? Let's find a relationship between nitrogen and NH3, or ammonia, if you want to call it by its common name. Nitrogen to ammonia is in a ratio of 1 to 2. This is so much easier. This is so much easier. I love this ratio idea. I love it. This would have made my chemistry days so much easier. Because I think Olivia was the one who said ratio, and as soon as she said it and the light bulb went off, I just thought, oh my gosh, how much wasted time in my high school chemistry classes. I was like irritated deep down inside, like all this wasted time. I could have been thinking about something else more interesting. Anyways, this relationship comes directly from the equation. Now let's bring the problem in, right? 5 liters of nitrogen, okay. 5 liters of nitrogen, that was sloppy. 5 liters of nitrogen, right? I'm just plugging in for the nitrogen. Cross multiply, what do we get? NH3 equals 10. What are we dealing with? Liters. Does that make sense? If I had 5 liters of nitrogen and I produce twice as many particles of NH3, I'm going to have 10 liters of that. This is the hardest, technically speaking, this is the hardest thing that a first-year chemistry class does. technically speaking, in terms of technique. It's called stoichiometry. I think I've used that term before. This is called stoichiometry, and this is what makes most chemistry students pull their hair out. I have a strong feeling that with ratios, we just got this on lock. And that makes me very happy. That makes me very happy. Took 5 times teaching the class to figure out the ratio thing, but hey, who cares, right? Because right now we got it figured out. Ooh, follow-up question. Follow-up question. How many moles of NH3 would that be at STP? Little poetry right there, right? Little end rhyme, if you will. How am I gonna, I mean, we know we got 10 liters of NH3. How am I gonna know how many moles that is? How am I gonna get from liters to moles at STP? Yeah, so we know that there are 22.4 liters of volume for a mole of any gas. So I have 10 liters, start with what you know, 10 liters of NH3, and then let's just do our conversion. Just like there's 12 inches in a foot, there's 22.4 liters in a mole at STP. Key, STP is key to being able to use that little statement. Because if it's not STP, all bets are off. So, 10 liters, well, 22.4 liters is 1 mole. So it's got to be about half a mole, right? Even just looking at the numbers, I'm just kind of ballparking it. Does anybody have a calculator who can assist us? 0.45. How beautiful is that? 0.45 moles of NH3. That, call me crazy here, but here's a situation where we have hydrogen, common, nitrogen, common, mixing together to make ammonia, which is in Windex, common. The Windex factory uses this equation all the time. This reaction is like at the heart of it all, because Windex doesn't work without ammonia. We ran this equation with 5 liters of nitrogen. We not only know exactly how many liters of ammonia we make, we know exactly how many particles. Think about that. We know exactly how many particles. And those particles are so tiny that you can't even see them with the most powerful microscope in the world. Yet we know that they're there. And we know exactly how many there are. You can run, but you can't hide particles, right? It's like that. You kind of feel that way. So there it is. Now, follow-up question. We can just build on this. Let's make sure we have time for a follow-up question. Oh, perfect time for a follow-up question. We have 0.45, blah, 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 STP. Okay, here's the question. How many liters would that NH3 occupy at 740 millimeters of mercury and 50 degrees Celsius? What if we weren't at STP? Now we know that at STP we had 10 liters, but the question is, what if we weren't at STP? Well, this is a case where we know at STP what happened, and we want to find out something about another state. This is one of those problems where we have state 1 at STP, state 2 at some other state. So let's do the comparison. Here's state 1, here's state 2. Gases change in the influence of pressure. Gases change in the influence of temperature. So state one. State one was what we knew. We knew we had what? 10 liters. We knew we were at STP. STP is what? 760 torr and a temperature 273 Kelvin. I'm telling you, next time you go to a doctor's visit, get your temperature and figure out 98.6 degrees in Kelvin. You will just, the nurse will get, she'll either lose her mind or think it's hilarious, one or the other.
Or she may have no idea what you're talking
And that's
about.
possible too. And then you can just make a joke to the doctor, because the doctor will know for sure. And then you can have a moment with him about the nurse. And because the joke went right over the nurse's head, but the doctor will follow for sure. So they're like, oh, I remember chemistry class. Anyways. This is what we had. We knew we had 10 liters of STP. The question is, how many liters? We don't know how many liters. At 740 torr and 50 degrees Celsius, that's going to be what? 323. Hey, that's a palindrome. Right? Palindromes read the same forwards, backwards. Yeah? Yeah. Okay, let's play the game. We have volume, pressure, and temperature. P1 V1 over T1 equals P2 V2 over T2. The combined gas law. If that's not burned into your head, start burning it into your head, because come next Thursday, ooh, it better be burned in, or else you may be in trouble. Right? Right? Because if you can't produce that equation, how in the world are you going to be able to solve that? Okay, so pressure 1, 760. Volume 1, 10. Temperature 1, 273. Pressure 2, 740. We had less pressure, so less pressure is going to give it more volume. We actually, well, our volume we don't know. And our temperature, we gave it more temperature, so that's also going to give it more volume. I bet the volume's bigger, right? We took pressure off of it, and we increased the temperature. Both of those things are going to drive the volume higher. That's a lot of computations, but ultimately it comes out to something pretty-ish. It comes out to an answer that's right. So you can do the cross multiples. What's 760 times 10 times 323? Or does anybody have V2 solved for it? It sounds perfect. 12.15 liters. Again, if you think about this, because you can always access in your mind, you can think, does this answer make sense? The pressure went down. So if I take pressure off, that's going to make the volume larger, and the temperature went up, so that's going to get the particles more excited and make the volume larger as well. So the volume went from 10 to 12. That's sensical, right? This is going to change our life. Yes, question?
When my sister, she goes here, she did a few problems like this, but we had to like take away water vapor pressure, but we have to do that for the test.
What do you mean by take away water vapor pressure?
From a given pressure, then we have to subtract the water vapor pressure for some of the problems.
That's, I'm not even sure what that's about. We'll talk about that maybe next time. Like if you can remember, or maybe ask me in study hall, we could elaborate, because I'm not even sure what that's referring to. Okay. Good class though. Thank you.
Thank you.
You're welcome.
I'll need you for just a second, Mark, when you're done.